We'll get started, so just some housekeeping before I start, and this is just a sanity check. So I'm told it's a 2-hour lecture, so we're done by 4, is that correct? And you're probably expecting a break of like 10 minutes or so, about halfway through. Okay, so we'll try and make that happen. At some point tonight, the slides will be put on whatever your internal system is called by Moodle? Moodle. It's cute. Okay. And this year I'm not privy to what is on the exam, so please don't ask me. You don't have an exam? Okay, maybe that's why. I was like, oh, they didn't ask me to write exam questions this year. Okay, then that preempts this. All the awkward questions about it's like, oh, do I need to memorize Word to Vec for the exam? Cool. So I'm Ed Graffenstedt. Normally Tori's here to introduce me, but apparently he's cramming on some paper. And I'm a research scientist at DeepMind. I'm also an honorary faculty member in the machine reading group here, so you may see me at other lectures. And I've been asked to give a lecture on deep learning for natural language processing today. If for some reason you were at the lecture I gave last year in this course, which you probably wouldn't be, you can leave because it's the exact same lecture. No, I tweaked a few slides. But, and it's a difficult lecture to write because we have entire courses centered around this title at Oxford, Cambridge, Stanford. And I'll give you some links at the end of the slides if you want to delve into the topic in more depth. They're excellent lectures. But deep learning for NLP, more than just a sort of subject or application of these techniques, is a very rich field indeed. So there's a few options about what I could do in a lecture, and one of them is try and wrap through 8 weeks of slides in 2 hours, but that would be somewhat unpalatable, and that I don't know how to wrap. Or I could just give you a sort of a little taster, and that's more what I've done in this lecture. So language is a fundamentally interesting problem. Why? Because some animals have some primitive forms of language, but it's one of the sort of key characteristics that distinguishes us from other forms of life. And it's one of the tools we use to formulate abstractions and communicate them. So more than just a way of getting things done on a day-to-day basis, it's actually part of our cognitive toolkit. It's how we think, it's how we talk to ourselves, it's how we make plans. So it's integrated into the higher form of intelligence that we sort of express. So it makes sense that if we are walking towards wanting to make artificial general intelligence or AI that is similar in ways to humans, that we'd want to sort of solve language. And I'm not going to solve language for you today because we are very much at the sort of first steps in this space. But I'm going to cover a few topics to give you a taste of some of the sort of questions that are being addressed for which we have models and where research is going. So I'll start off by talking a little bit about how we can build representations for words, because they are, in many respects, the sort of common building blocks of our languages, although obviously we sometimes want to deal with characters or ideograms. I'll talk a bit about language modeling, so kind of the unsupervised learning of natural language understanding, and talk a bit about conditional language modeling and how we can use language modeling objectives to learn translation models, which will bring me to sequence-to-sequence models with attention. And all these things are building on things that either you've seen in previous lectures in this course or have yet to see, because I don't remember exactly the order of the topics. I'll talk a bit about a few of the applications of these methods to natural language processing and understanding, and end with a few slides on composition and classification. So let's start by talking about word vectors, which is, for some people, a fascinating topic, but certainly not my favorite. So I'll try and simulate enthusiasm, but it's important to understand it. So in natural language natural language understanding and processing, we want to be able to deal with text typically, and that might come from speech-to-text synthesis or from the vast amounts of text we see on the internet. And text is a sequence of discrete symbols, so words or characters or ideograms in other languages. So we need to build a representation for this text if we want to feed it into our models, especially neural networks, which expect vectors as input. So the very naive representation of a word, if you wanted to sort of be as unbiased and general as possible, would be simply to have vector space, which is the size of your vocabulary, and each word is a one-hot vector in this space. So for example, you assign to every unique token an index, and you set one, and to produce a vector for it, you put a one at that index position in the vector, and everything else is 0. So this might sound really naive, but it's in fact fairly successful in very simple systems. So classical information retrieval, which sort of, I guess, over the years evolved into technologies like Google's, used this representation to do document retrieval. So in classical information retrieval, the document and the query vectors are just going to be superpositions of word vectors. So you want to produce a representation for each web page, you simply sum all the vectors of all the words in the web page, and that gives you a single vector, the size of the vocabulary, with trivially the counts of each word that occurs in the document. Likewise, your query you can treat as a small document, which you're going to execute against your retrieval system, and then you take some similarity metric amongst the vectors, like their inner product or the cosine distance, and you return the documents or the k documents that give you the highest score. And that's information retrieval in like a nutshell. Similarly, for like word classification problems, like document classification, you can do very naive sort of count-based metrics along this dimension. So the obvious issues are that this is a very naive sort of representation. So there's nothing in the representation that tells you about similarity, about semantics, about relations. So as humans, we understand that cat and kitten are different words, but that the concepts they point to have some sort of notion of similarity. But in this sort of representation, they are literally mathematically orthogonal. So they're sparse orthogonal representations. They have no semantics. And obviously, we can do better. So we want richer representations that express semantic similarity. And before I jump into how we do this with neural networks, or at least sort of vector-based machine learning models, I want to give you a bit of the context for how these models came about. So there's an idea that was postulated by several thinkers in the 50s, including the philosopher Wittgenstein in some fashion, called distributional semantics. And it's the most famous quote in relation to this idea of semantics is this quote by J.R. Firth: "You should know a word by the company it keeps." The idea is to understand words, we sort of look at how they're used, what sort of other words occur around them, and this gives us some information about their syntactic and semantic roles. So there are three main approaches to distributional semantics that involve producing dense vector representations based on the context or use of words, rather than these very sparse orthogonal representations we have by taking one-hot vectors. There's count-based methods, and we'll start by describing those. There's predictive methods, which are sort of proto-neural networks, but mostly bilinear models. And then there's task-based or end-to-end sort of approaches to learning representations, and I'll sort of briefly mention those towards the end of this section. So count-based methods, again, are probably not something you're going to be wanting to implement because we have better ways of doing this, but it's important to formulate high-level intuitions about what word vectors are and why we build them the way we build them by looking at how people used to do that up until probably the late 2000s. So for count-based methods, you're going to start by defining a basis vocabulary sea of context words. So this could be all the words in your vocabulary if you're particularly ambitious and have a lot of memory, but typically you're going to want C to be the sort of the salient context words that you expect to be informative. So people have a variety of heuristics for this. You take maybe the top 10,000 or top 5,000 words in the language. Maybe they exclude stop words like the and because those don't tell us really that much about like the words they co-occur with other than syntactic markers. But so the first hyperparameter is basically your context vocabulary. The second sort of hyperparameter for this approach is you define a word window size W. So under the most naive approach, we're going to consider the context to be W words on, like 3 words on either side of your target word, or 4 words or 5 words. And obviously the size of this window is quite meaningful in terms of the representations you're going to be producing. And once you've defined those two things, you simply count the number of times each basis vocabulary words occurs W words to the left or the right of each instance of a target word for which you're building a representation. So context words might also be target words for another part of your model. But the target words are the words you're building representations for at the moment. So you iterate through your target words that you want vectors for, and you simply collect counts like this. and you form a vector representation of the target word based on these counts. So to give you a little illustration, let's imagine we have a little snapshot of the corpus, and we have target words kitten, cat, and dog. That might occur one or more times. So we collect here 3 words on either side. And let's say that we have a small basis vocabulary based on our prior knowledge of what we're looking for, which is the words bit, cute, furry, loud, meowed, purred, ran, smell, small. So we don't include things like and or the. And so we simply first collect for each target word the context words. So we see that kitten has cute, purred, small, meowed. Cat has cute, furry, meowed, etc. And we can just turn those into vectors by putting the counts as ones or the actual count value, which happen to be 1 for convenience, at every position in the vector that we mapped that context index to. So, sorry, I feel like I rushed that. So obviously, each context word has a unique index, and then we set the count for that index in the vector to the count, and 0 if it doesn't occur in the context. So that just gives us these representations. And now you can see in contrast with one-hot representations, kitten and cat obviously have some overlapping ones, as do cat and dog. So once we have collected these vectors, we can use any sort of distance metric, like the inner product or cosine distance, as a similarity kernel for the concepts that the words stand for. So we can check that, for example, using cosine similarity as a distance metric, we can check that the similarity between kitten and cat is 0.58, and the similarity between kitten and dog is 0. And the similarity between cat and dog is 0.29. And these numbers don't have a probabilistic interpretation or anything particularly strong, except we know they're bounded between 0 and 1. But what we observe here is that we now have, through this very trivial count-based methods, the notion of a semantic continuum. And that it's not the case that everything is only identical to itself, but some concepts are more identical to others. And obviously this is handcrafted to match our intuitions, but this tells us just from looking at words that occur that kitten and cat are probably more closely related concepts than dog and cat or dog and kitten, respectively, just based on looking at how they're used. So as a quick reminder, cosine similarity obviously is nice because it's norm invariant, so it doesn't matter how, if some words might be very frequent and have very high counts, and some words might be infrequent and have low counts, but by using cosine, we can compute similarity by just looking at if they're pointing in the same direction. So it's a nice auto-normalizing measure. So what's wrong with count-based methods? Well, there's a lot of reasons why we've gone beyond them. The first is that not all features are equal. So first we have to distinguish counts that are high because the words are particularly informative from counts that are high because the words are independently sort of frequent in context. So some words, for example, that's a good example, like red or small, are going to be very frequent across a variety of descriptors of animals, for example. So they might not be super informative compared to sort of like freckled or sort of carnivorous. Those might also be frequent. But you get what I mean, right? So some words just happen in a lot of contexts, so aren't very good at distinguishing particular concepts. Some words are going to be very identifying of particular concepts. And obviously this depends on your task, so it's difficult to sort of have a nice ordering of those. So there's normalization methods that allow us to sort of like post-process or count-based vectors in order to sort of try and capture that idea, that some things are going to be, some context words are very informative in your corpus and that they allow you to distinguish concepts, and some just become part of the background noise and maybe should have been removed from the context in the first place, like and or, which we heuristically remove. So we can take like the term frequency divided by inverse document frequency is a common normalization method. There's point-wise mutual information. And I won't go through describing these in detail because you can just look it up in survey papers if you're very interested. But it's good to see that there are some methods that try and sort of capture this sort of semantic contribution of context words. And some are in fact quite sophisticated in that they remove the need for norm invariant similarity metrics by turning the vectors into probabilities. But there are perhaps like easier ways of sort of addressing this sort of problem. So one of the easier ways to deal with the problem of having to pick your features, so by picking your context words very carefully and thinking about how to renormalize them, is to not have to do that. So instead of having a very carefully hand-engineered feature space, which is effectively what we're doing with traditional distributional semantics, we can do what we do well in deep learning and neural methods and just functional approximation in general, and jointly learn the features from the data. So before I jump into how that works, let me give you the intuition of an embedding matrix, which some of you, if you've implemented anything involving text, will be familiar with as an operation. So all those vectors that we collected in that previous slide can be sort of stacked into a matrix since they're all the same length. They're the length of the number of context features I've defined, right? And this matrix is what we'd call an embedding matrix. We call this an embedding matrix because if I take the one hot vector for a word, right, which is that sparse representation we started with, assuming that the index, so the index at which it's 1, corresponds to the row it's at in this matrix, then trivially by taking the multiplication of the one hot vector by the embedding matrix, I retrieve that dense vector that we collected counts for, right? So here I've separately done the sort of, I've pre-learned my embedding matrix through the count-based method, but there's a simple idea that there's a differentiable operation that maps a sparse, discrete representation of the token, of the symbol, to a dense representation of its semantics. Whoops. And all the methods that we're going to be seeing from here on are going to involve, instead of using count-based methods and heuristics to define this embedding matrix, we're going to learn it through backpropagation. So symbols are unique vectors, and representations are sort of the embedding of those symbols within our semantic space using this embedding matrix. Are there any questions so far? Yes?
So how to deal with multi-sense words?
So words that have multiple senses are an interesting and open problem. So a lot of the approaches you'll see in natural language processing with neural nets, even more sophisticated ones, assume that there's a single embedding for the word and that you're going to have to deal with that. So, I mean, if you want to, there are probably more sophisticated ways. If you have external information, like, for example, you've done a word sense disambiguation step by using a pre-trained pipeline like Stanford Core NLP, right? You could assume that you're going to do pre-processing and you're going to build separate representation for each senses of the word. But that involves the input of a particular bias because you're using the bias presented by your tool into your model. Another way you might look at it is to say, okay, I'm going to have a single representation for the symbol, that's a dense semantic representation, and I'm going to trust that my model can represent the totality of the senses in that vector. And obviously that means that if you use the vector on its own, you're not going to be able to disentangle those different senses directly. But if you're inputting that vector into, let's say, a recurrent neural network or a ConvNet or WaveNet, et cetera, things that can capture long-range dependencies and affect information flow, maybe the previous context will allow you to sub-select parts of the vector relevant to one sense versus the other. So for example, if you have bank, right, which might be a riverbank or it might be a financial institution, and you're doing translation, right, and the previous 10 words were like, I went down to the, wait, no, that doesn't disambiguate. It's like I took my wallet and went down to the bank. When you read bank there, because of the presence of wallet in your context, maybe a network could be sufficiently intelligent through a good training objective to learn to gate part of the representation relevant to riverbanks out and only include the part relating to financial institutions. But that's always putting a lot of trust in your model. So maybe there's a more clever way to do that by modeling using lane variables like the plurality of senses. So it's a great question, but it's open research. Yes?
I was just going to say, does that sort of requirement require you to have quite high dimensional word vectors if you want to disambiguate? Otherwise we're cutting off presumably quite a lot of dimensional.
Yeah, because so if you're, for example, if you're doing count-based vectors are nice because we can directly interpret the features and you can think about these issues in an idealized context. And obviously, if we have if we don't have many context words, right? Some context words are which might be informative with regard to distinguishing bank from, let's say, train. Might not be representative, might not be useful for distinguishing both senses of bank internally because they occur in both, right? In which case, suddenly you have a useless feature when you have a useful feature with regard to like separating words that have different tokens. but different types, but you have a useless feature with regard to the disambiguation task, and indeed, the solution might be, I need more and more context features. But increasing the context window size also includes noise, right? So you trade off one problem and create another, which is the difficulty with not just that approach, but also the neural nets. So it's definitely an open problem, is how to deal with sense plurality or ambiguity. Any other questions? Great. So let's talk a bit about how we can learn this embedding matrix. So neural embedding methods in general, and when we say neural embedding methods, we're including things like word-to-vec, which is not per se a neural network. It's a log bilinear model, but neural network is taken today to refer to pretty much anything with a matrix and backprop. So if someone's super pedantic, I don't care. So the general method, and obviously there are approaches that don't fit this mold, kind of fits this pattern. We're going to collect instances of a word that we want to build a representation for in our vocab. And so obviously this is our target word as seen previously, and we might have many target words we're training in parallel. But let's treat it somewhat in isolation for now. And for each instance, we're going to collect its context words. And so context words here could be something like we did before, which is like using a k-word window, where again, the size of making the window large might give you a more informative context, might add more noise. Making it too small will remove noise, but make it less informative. Or you might do something smarter, like say it's going to be dependent on syntactic information like parse, or just I'll limit it to sentence boundaries. Or if you're using more sort of modern models like recurrent neural networks, you might just say I'll just figure it out as we're going along. You don't need to explicitly specify the window. So, but for the methods we're going to be looking at now, this window is usually explicit, and we're going to find some scoring function. That's going to be a function of the token word, its context words, so the words that occur with it, and some parameters, which typically will have an upper bound on the output, so that we want to maximize it. And we're going to define a loss, which is going to be across all the words that we want to build representations for, and across all the instances of those words, the sum of the negative score. So by minimizing this, we maximize the score across all the words we want to build representations for. And this is nicely linearly separable. We're going to estimate then, through usually a gradient descent-based method, the optimal parameters of whatever the scoring function is, which we might not reuse. We might just be training that for the purpose of training our embedding matrix, and the embedding matrix itself. And we're going to use that estimated E as our embedding matrix. So before I jump into some examples, the choice of your scoring function in this context, which is going to be the objective against which you're going to be building your vectors, is very important, especially in these sort of more hand-designed methods we'll be looking at, and less when you're doing task-based embeddings. So it's easy to design a useless scorer. So you can easily and accidentally design a scorer that ignores the output, or that ignores the input, or that doesn't have a bound on the output. And I mean, the trivial example of this is if you're using a scorer that allows all the embeddings to go to 0 and then minimizes your loss, then you create a useless score. And this was the sort of trap that a lot of people fell in the very early days of neural networks or function approximation-based embeddings. So the ideal desiderata for your scoring function here is that it has to obviously embed your target word using the embedding matrix, because if it doesn't, then what are we backpropagating? How are we updating the embedding matrix through backpropagation? It needs to produce a score which conceptually at least tracks a function of how well that target word is accounted for by its context. So how well the context explains the presence of that context word, or vice versa, how well the presence of that target word explains the context. And we'll see some examples of this. And ideally we would like that, we assume that we're training this on natural text, on text that we've obtained from humans. ideally the scoring function encodes the requirement that that word is the best word that could be there. So that by replacing it by a random other word should lower the score. That the scoring function reflects that that word belongs there more than any other word in your vocabulary. So these are all like strange assumptions, but we'll see how they translate into reality and into particular scoring functions. And finally, this should produce a loss which is differentiable with regard to the parameters of the scoring function and the embedding function. Otherwise, you're going to have a hard time training it through backpropagation. And this is probably not the sort of thing where you want to jump into reinforcement learning. So one of the early approaches to embedding by using a neural network is neural embedding models by Culbert and Weston. So this is a really beautifully titled paper called Natural Language Understanding from Scratch, or Natural Language Processing from Scratch. So the from scratch thing is beautiful, beautiful marketing. And, and it's a cool paper. I mean, so this method is not something you'd use these days, but this really, I think, like started a revolution in natural language processing by making people realize, maybe we should be looking into these neural networks again. Obviously, people were looking at neural networks in like the 70s and 80s and natural language processing, but this made people think, let's do it again. Most of the authors working on this are now sort of quite senior researchers in Facebook AI research or in DeepMind, including Corey Kvuluku, who's the head of the deep learning group. I'm pretty sure was on that paper. So the approach here is simple. We're going to start by taking our embedding matrix, which again is just a matrix you're using to project one-hot vectors into dense embeddings. And we're going to embed all the words in the sentence. So we're going to produce vectors, for I'm assuming that you can see, I usually like to point. I can point. So you're going to produce vectors for each word in the sentence using your embedding matrix. So that's the first differentiable step. You're going to then use a function that is a shallow convolution, so a function that you can repeat because you might have different length sentences, is going to convolve those into a single representation by doing a projection across like 3 or 4 or 5 or W words, and then summing all those particular applications of that convolutional map. So that's like a little convnet, if you will. And that produces a representation. Then you might apply nonlinearity, and you then project those into a scalar using an NLP of however many layers you want. There is no point in memorizing these architectures, by the way. This is just to try and, all these are for the purpose of giving you an intuition about how embeddings are. Now, this is fine because you don't have an exam, but this is usually where people ask me, it's like, am I going to have to repeat the specific details of this in the exam? And that would be pointless information for the examiners. So that's really the whole idea, is like barf out some vectors using your embedding matrix, project them into a single vector, map that vector into a scalar, which is your score. And the overall network is therefore modeling just a scoring function over the sentence. So if you were just at that particular, if you stopped there and you said, okay, let's use that scalar directly as our score, and I want to, let's imagine we're treating it as a loss, for example, and I want to minimize that loss. What could I do? I could just, for example, set my embedding matrix to just be a matrix full of zeros, right? Because then that would, if that's like the lowest score I've defined, that will just trivially minimize my loss, but I won't produce anything particularly useful. So they have to produce a scoring function or an actual loss based on this scoring function that prevents the network from ignoring the output or producing sort of degenerate or trivial solutions, because we want the vectors that we produce here to be informative. So remember, I told you one of the desiderata for these scoring functions is that they sort of show that word accounts for the context, that replacing it with a random other word that each word accounts for the context, and that replacing it with a random other word should be less good according to the scoring function. And so how they transform that thought into a differentiable loss is that during training for each sentence, they're going to sample a random corruption of that sentence by replacing a word at random. So we have our true sentence S, and we have our distractor sentence, which is identical except that one word is random, Z. And you're going to minimize the hinge loss, which is by taking the difference between the scores of the sentence with its distractor, -1, because we want to maximize the difference. Yes, but up to a point. So the hinge just says it's like there's no point in making them too different. You just at least want to maximize it within bounds. And so this means that if you do something trivial like map everything to 0, then these are going to be identical, and so then your loss is going to be 1, and you can't minimize it further. There needs to be some difference in the representations that yields a difference in the score. Man, this is kind of, you can read this, right? Okay. There needs to be some difference in the representations leading to a difference in the score that's significant enough that this gap is close to 1. And then if they're significantly different by, for example, having a model that's getting a little too excited making vectors like maximally orthogonal, then you don't get any benefit thanks to the hinge loss objective. So they still need to be vaguely similar because they are very similar sentences. They just have a corrupted word. So the interpretation here is that representations that you're learning in your embedding matrix are carrying information about what neighboring representations should look like. So this means that if you're like changing a word, then the model should be able to capture that that representation doesn't belong there. That according to the words that I have seen, that some word stands out, and I can tell you which one, at least to the point of giving a lower score than if that word had been the correct one. So by setting this objective, which seems really simple, right? It's just basically have a forward function that projects everything into a score and define a hinge loss. We're producing something that looks a lot like the distributional hypothesis, that the sort of low energy configuration that gives you sensible scores means that the vectors contain information about what their neighborhood should be like. So you know a word by the company it keeps, literally. But this is the neuralification of that idea. It's a sensible model because it kind of fits high-level intuitions about what we were doing in distributional semantics. But it's fairly deep, and this is deep by the standards of the day. Obviously, this stuff's pretty trivial to run on a GPU these days. But it's fairly deep compared to some other methods, so it wasn't cheap to train. And the convolutions that you use to produce that representation are going to capture very local information. So that's kind of like that's like a window size hyperparameter, and it's very sensitive to that. So another approach, which is still popular, which people still use and continue to re-implement in tutorials, is word2vec. So word2vec is in fact two models, skipgram and contextual bag of words. And how am I doing for time? Pretty well. So the approach here is much simpler and significantly more GPU friendly, if you care about those things. So to start, we're going to embed context words, and we're going to add them. And we are going to project that vector that we've had from simply adding all our context words in our window. Sorry, got distracted by that bottle. So step 1, contextual bag of words. We're going to take a window around the target word that we want to build a representation for and remove that target word. So we're going to ignore it for a second. We're going to embed the context word, so all the words except the word I care about, and add their representations into a vector. So that's a very simple operation. And then we're going to project that representation back into the size of the vocabulary and do a softmax operation. So that is going to essentially produce a distribution over, what the context word could be, what the removed word could be, given the context. So we have a very clear probabilistic interpretation of this. And on top of that, the fact that we're just taking a sum and then projecting means that we don't need that we can move that, we can do little optimizations and move the sum inside the softmax, do the embedding operation once and then project after doing the sum, which is nice and efficient. And the objective here doesn't need any sort of very careful handcrafting. It's just minimizing the negative log likelihood of the correct word. So we just take the cross entropy with regard to the correct word that was held out of that distribution. So it's nice, and so we often in language talk about negative log likelihood because it's just minimizing the negative log likelihood maximizes the log likelihood, which also maximizes the probability of the correct label. So these things are all equivalent, but you get to do it in log space, which is stable. So this is nice. It's a nice model. It's all linear, so it's very fast, and it's a very cheap way of applying just one matrix to all the inputs. So rather than having to sort of take the sum of the projections and then doing the softmax. Historically, how this was trained was by doing negative sampling instead of doing the softmax directly. But today, on modern computers and with libraries like TensorFlow, you can have a fast and stable softmax on GPU and use that instead of any fancier training mechanism. So actually, minimizing the negative log likelihood directly is the preferred option, and it's much more stable. There's a bunch of variants that have been explored to this idea of a contextual bag of words. So for example, Wang Ling and Chris Dyer in 2015, instead of just taking the sum of the context vectors, transformed the context vectors by a matrix depending on where it is positionally with regard to the target word. And that can be seen as like weakly capturing possibly slightly syntactic or word ordering information. And there's a whole, about like 2 or 3 years worth of ACL papers on the topic of word embedding, doing it in a more sophisticated way, which are all basically variants on this approach. The dual to the contextual bag of words, where the context needed to predict the word, is skipgram, and this is possibly the more popular variant in Word2Vec, where now you are going to produce an embedding of the word that you're trying to build a representation for, project it into the target vocabulary, and predict all the target words in the context. So that's literally the whole idea is take your word, embed it, and then project to the vocabulary. That gives a distribution over words that might be in the context. Take the negative log likelihood of the context words is going to be the negative log of the product of the probability of each context words given the target word that you've observed. And that nicely goes out to sum. So you can basically just do it in one pass and read the logits off your single projection. So it's very efficient to implement, and that's possibly the main reason why it's preferred. So super fast approach. There's just one embedding operation, one projection. Read the probabilities from the softmax. And there are similar variants to contextual bag of words. So conditioning on the position rather than just producing the probabilities of the target words willy-nilly. But obviously, you're always adding computation, adding parameters to do these. So in general, in these approaches, we see a nice sort of trade-off between the efficiency of the method and a more structured notion of context, which I guess is the easy way of summarizing all the work that happened after Word2Vec. Is let's add more computation and more structure and get better representations, but it might A, add more bias, and B, certainly adds more computation. So as an engineer or as a model designer, you need to pick one based on those constraints. So that's sort of summarized. We've sort of seen I'll take questions in a second, but we've sort of seen a quick history of word embedding methods more from a sort of linguistic perspective, count-based methods, and we've seen how those can be turned into sort of efficient little neural networks or function approximators to remove the need to like think about what are my context words, what are my stop words, and let the data just pick those things for you. So you lose interpretability in that the dimensions of the vectors no longer mean it's like, oh, I've seen this context word this many times, but on the flip side, you don't need to make that decision. So win some, lose some. Any questions on this part of the lecture? Yes?
I was just wondering, in your first model, in the Colabert model, where you've got the convolutional layer,
Yeah.
whether the kernels that kind of learn end up, like, whether there have been investigations where they actually capture sort of syntactic, dependencies. Is there a kernel that learns, to look two words behind and
That's a good question. Probably. So people have worked on applying convolutional nets to prediction. To a variety of approaches, including machine translation and generally sequence modeling, sequence labeling, and the sequence classification. So, in particular, Jan LeCun's group at NYU, now Cashbrenner, the people behind WaveNet. Whether people I'm not aware of any individual work that has tried to do exactly what you mentioned, but it sounds like something that I probably heard someone talk about. So I'm unfortunately showing my lack of expertise by not being able to point you to a paper, but if no one has done it, please do it, because it sounds like a sensible way to try and interpret a neural network. Yes?
You mentioned that instead of taking a dumb window around the word, you can rely on, say, I don't know, a dependency tree.
Yeah.
Is either given or could be learned. But I feel like in papers I've seen that's not that common? I mean, does it not improve?
Yeah, so I mean, so relying on dependency trees was a very popular approach when we were using count-based methods because you're constraining something to, you're only counting as part of the context things that had some syntactic relation, which you'd hope would express a semantic relation. So a lot of work in the 90s did use this kind of approach. In the sort of more neural approaches to just word embedding learning, I think you see a slight improvement by conditioning on word position. So Wang Ling's paper kind of shows this, but it's not so amazing that people care about it a lot. I mean, people have focused on incorporating syntactic information at a higher level when you're building sentence representations, and often that's sufficient to learn words extrinsically just from like the end objective. Yes, I should have mentioned, I'll get back to it later in the lecture, but the third approach to learning word embeddings is to say, I have an embedding matrix as part of my general model, whether it's sequence to sequence or sequence classification or all. I have an objective like learning to translate or learning to classify sentiment from a sentence, and I just backpropagate into my embeddings and learn them from scratch. So instead of pre-training your embeddings, you can just do that. I think I'll probably repeat that later on, but I hope that answers your question for now. Any other questions?
What was the thing you said?
Dependency tree.
Yeah.
Just like a parse tree.
What's the dependency tree?
Dependency tree is a form of parse tree. So, for example, you can translate CFG parse trees into dependency trees, which are DAGs expressing that something is like the direct object of the verb versus like the subject. So just another way of expressing syntax, syntactic relations in a sentence. Okay, so let's jump into discrete language models and then we'll take a break. So we've seen words. Let's move on to how we can deal with larger units of text. So have you had a lecture on language modeling already? With RNNs? Okay, great. You'll probably see this again at some point in like either, has Oriol given a lecture yet? Did he talk about language modeling? You did? A little bit, okay. We'll revisit this. It's like hearing things twice is great. You'll be like, starting to remember it. Okay, so language modeling is, we've talked about like scoring sentences based on like whether a word belongs in it or not. Language modeling is a significantly more powerful objective in that it's effectively what we're doing in unsupervised learning, which is you have some data and you model the probability of your data. So you want to, for unseen sentences or unseen data points or sequences or unseen images, unsupervised learning, which gives you an explicit density model, should be able to say, okay, here's the probability of this data point according to the distribution of data I've seen during training. So that's exactly what language modeling is about. It's about estimating the joint probability of a sequence of symbols by learning to maximize the probability of a corpus of symbols. So this probability of a sequence is usually decomposed left to right, but obviously it's mathematically correct to also decompose it right to left, and you might want to do this if you're doing language modeling for, say, Hebrew. So you decompose it left to right as the product of the probability of the next token given all the tokens you've seen so far, which we usually write in some sort of compact notation like this. So this sort of underscore 1 to I minus 1 means all those tokens from index 1 to I minus 1. So in practice, what we're trying to do with a neural network or with other methods in language modeling is we want to estimate this conditional probability, what the probability of the next token given a possibly unbounded prefix of tokens is according to the data we have. So before we jump into neural networks, the most popular approach to language modeling, in fact the state of the art until probably 2 or 3 years ago tops, was n-gram language models. So the n-gram language models try to address this issue. The probability we've just defined depends on a variable length, unbounded history of our sequence. And how do we model that? Because we might have different lengths and we want to be able to, we can't just, for example, record every particular instance and just pretend that we have a variable length probability distribution in a table. So one solution, if we want to use tabular methods, is to introduce an order k Markov assumption. So an order k Markov assumption in sequence modeling means that I'm going to condition my decision about what to do next, so which symbol to emit next, on, at most, the previous k symbols. And now this is an approximation of the actual objective, which is on an unbounded sequence, an unbounded prefix, what the probability of the next symbol given an unbounded prefix. And we're reducing that to estimating the probability of the next symbol giving the previous k, if they exist. So we can, again, we see that count-based methods show up all over the place. We can estimate this probability using counts. So very trivially, we can have a tabular approach where we're going to collect all k plus 1 grams, so all sets of k plus 1 words that occur in our corpus. So that's kind of having a moving window sliding over our corpus and recording the contents of those window at each time step. And then to produce the probability of the next word, so of the final word in that window, we're simply going to count how many times we've collected the k-word prefix divided by the number of times, how many times we've collected the exact tokens seen in that window divided by the number of times we've seen the k-word prefix. So this is pretty easy to derive by the definition of conditional probability if you really care to understand it in detail, but I'll leave that as an exercise. So the problem with this approach is that it's very sensitive to the order of our Markov assumption. If k is too small, then the language model is terrible. So trivially, when you had, everyone calls this like iPhone poetry or something, which is frustrating to linguists who have this idea since the 50s. But if you have predictive text and you just predict the next word, you can generate sort of vaguely sensible sentences of English. But you quickly notice when your language model has a very low Markov assumption, in that the words being predicted seem to depend really specifically on the previous words. So if you say I am, and then you'll see like a list of like hungry, lost, on my way home. Those will be very likely suggestions given order 2 Markov assumptions. But if you have something where it's clear that you're talking about, I don't want to use the bank example. I should have covered. If you have a prefix, if you're starting a conversation that says it's like you came home at like 2 o'clock in the morning last night, therefore I am, and you don't want to say hungry at that stage. You want to say I'm angry or annoyed because your partner's woke you up in the middle of the night. To predict annoyed, it would be very helpful to be able to take into account more than just the previous 2 words, to like look at what's been happening at the beginning of the sentence, because that's probably going to shift your particular bias towards talking about being annoyed or sad rather than being hungry. Does that make sense? So a larger one, obviously a larger k, a larger Markov assumption allows you to condition on a longer context. A smaller k would probably trivially yield a fairly limited language model. But when k grows, the problem is that these particular counts are going to become more and more are going to become smaller, because if we have, for example, even if you take millions of web pages, a 10 gram, so 10 words, a 10-word sequence is likely to be attested only once in that. Even if you take 5 grams, and Google has an n-gram explorer, which you can actually collect counts from if you want, are probably going to happen a few thousand times. Some 6 grams or 7 grams, only a few hundred times. So as you grow your order n Markov assumption, the counts are going to become poorer and poorer estimates of the actual probability of that sequence due to this sparsity issue. So in a sense, larger k. So we often talk about an order n Markov assumption. I've used k here because I used n in other places. But the larger the order of your Markov assumption, the better your language model should be, but the sparser your table is, so therefore the worse your estimation of the actual probabilities becomes. There are some solutions to address this, like smoothing. So Knesser and Ney came up with this idea in 1995. But overall, count-based n-gram models suffer from sparsity even with more sophisticated and more robust statistical methods. Nonetheless, until I guess really big LSTMs on GPUs came along in 2014 and 2015, these were still like the best language models we could train. So should we take a 10-minute break now and come back at 3 or 4 past? We've covered so far how we can learn representations of individual words. And a lot of the methods that we've investigated are, in a sense, unsupervised, in that They're building entirely on an objective defined over explaining the data as it's observed, some text from a corpus, in order to build representations of those words. And then what do we use these for? Well, we're going to see throughout this lecture and also in the lectures that you've seen in Oriel's lecture, and I think, has Alex Graves given a lecture yet?
Next week.
Okay, next week. You might see also uses of word embeddings there. I don't know what exactly he'll talk about. But training your word embedding matrix through these approaches is an example of transfer learning. It's an example of saying, okay, I have a lot of data that's not labeled, and I want to build good representations for my words, and then I'm going to use those as the initial state of my embedding matrix in a translation model, or in a sequence annotation model, or in a sentiment analysis model, and I might fine-tune it by updating the matrix while I go. Or I might freeze it and say, I'm transferring knowledge from a larger corpus into this specific task. And because I've just noticed that I don't mention this in detail later in the slides, let me just quickly point out before diving into conditional language models that this choice is actually quite an important one. So when we have a lot of data and you're doing some extrinsic task like translating or recognizing textual entailment, typically what works best if you have enough data is to just randomly initialize your embedding matrix and learn it through backprop alongside everything else in your corpus. But for some tasks where you do not have enough data, and enough data really depends on the task and on the signal you get from the annotation, it's found that fixing your word embedding, so not updating that during your model training and updating every other part of your model, yields significantly better results, and that it's less likely to overfit because those representations contribute something a bit more global from outside of your training data in that task. So especially like in question answering, when you may have heard of or will be told about like the squad data set if you work in question answering by Stanford. Overfitting is a very common problem there, and I think uniformly across the state-of-the-art models in the data set, people will pre-train their word embeddings with Word2Vec or GloVe, which is another approach, and then freeze them. So it's it might seem almost irrelevant given that you learn, neural networks are end-to-end differentiable, so why not just learn my word embeddings along with everything else? But if there's one area where transfer learning has worked quite well in natural language processing, it's word embeddings. Okay, so let's jump in. So we've seen how count-based methods not only could provide very naive ways of producing semantic representations of words, but also of estimating the likelihood of text. We're now going to move on to seeing how neural networks can do this, and how not only can they do this better, but they allow for the specification of conditional language models because they produce abstract representations of features of anything, any conditioning information. So therefore, we can express much more. We can shape the the probability distributions according to specific tasks instead of just doing unsupervised learning. So before I jump into that, let me talk a bit about how neural networks or related approaches have been used to do unconditional, so normal language modeling. So it turns out you can estimate the probability of string, like we do in traditional language count-based language modeling, by learning a function over the probability of the next word given the previous k word, so with the same order k Markov assumption, using a neural network or a log bilinear model, which is like a neural network but without the nonlinearities. So the structure of these is like that. So that conditional probability, which is really the main thing we want to learn from the data, is going to be estimating for embedding the token of each word in the history. So each word in our prefix, we will simply embed it, and we'll project it according to a position-specific matrix. So the third word before our target word will be projected using will be embedded using the same embedding matrix as the second word and as the first word before, but they'll go through an extra linear projection which is dependent on their relative position. So that we're capturing both the sort of context-independent semantics of the word through the embedding matrix and the context-dependent semantics of the word through that positional matrix. And usually you'll have a positional bias. It turns out the trend these days is to say that biases don't matter so much, because especially if you're learning everything end to end. But it's nice to include them somewhere. So you embed each word in the context. You project them by position-specific embeddings. You simply take the sum of the result, and then you put that through a function sigma, which is either nonlinearity or something else, and I'll describe that. You put it through a projection back into the space of the vocabulary, so this is the logist categorical distribution over what the current word is, and the softmax operation turns that into the parameters of a categorical distribution, which is exactly what we're modeling here. So the high-level idea here is you simply embed the words, you project them into a single space depending on their position, and then you predict what the next word should be. If sigma here is a nonlinearity, like a sigmoid or a tanh, then this is the neural language models by Bengio et al. In 2003, which I guess was one of the sort of resurgence of like neural language modeling before RNNs and LSTMs sort of made a comeback. And if it's the identity, it's what's known as a log bilinear language model, which was developed by Andrew Nee and Jeff Hinton in 2007. And the fact that these are both roughly equivalent is only something that has been observed since then. So it's not like they just took an idea and made it simpler, right? It came at it from a slightly different direction. And the sort of joint properties have been explored since. Obviously, if it's the log bilinear models are advantageous in that they don't contain nonlinearities. So if you're doing the cross entropy in log space, you don't need to actually take the softmax during training, and you can be very efficient and do this on a GPU super fast. And for some reason, people aren't super into log bilinear models anymore because we can train deep LSTMs pretty fast on modern computing architectures. But if you really wanted to have a model that was just good enough and super easy to run on, let's say, a phone, it's surprising no one's looked into revisiting log bilinear models. Obviously, the hip thing these days is recurrent neural networks, and you've had a lecture on recurrent neural networks already, right? So I'll just remind you kind of how these work. So whereas log bilinear models and neural language models by Bengio from 2003, like remove all the issues of sparsity from count-based methods by saying we're just going to use dense vectors and learn the features independently. So just in how we were removing sparsity and feature engineering from word vectors by using neural embedding methods, they're removing the feature engineering and the sparsity issues from the language modeling side of things through the same method. But they still rely on this order k Markov assumption, in that you're still just doing this, projecting the previous k words into the same space, and you're ignoring the prefix before. So this isn't exactly modeling the total probability of the data. Recurrent neural networks allow us to relax this assumption by not specifying k explicitly. So technically, you've seen neural networks have as basic construct this recurrent cell, which at each time step takes a projected version of the input. So this would be the input word, and you embed it, and you put it through a linear projection, and then you add it to your hidden state, perhaps with some gating if you're using an LSTM. And then condition on that input and your previous hidden state. If you're doing something like a GRU or an LSTM, there's some complex gating architecture in here that updates the internal state, and that gives you your next state. And based on that next state, you also are going to project back into the vocabulary and predict what the next word should be, for example. So the activations at each time step of this recurrent cell, which we unfold over the sequence to produce a sort of variable size network with repeated parameters, model the information of the entire prefix, of all the words that happened before, in theory. In practice, they're still modeling some bounded history. So they're only going to really remember information. I mean, so trivially, this is a fixed size information reservoir. Even if you're using continuous values, they're going to be, discretized at some point in your computer. So there's no possible way that this can learn to just like capture completely unbounded information from history and get something out of it, right? At some point, it'll get lost in the noise. So in practice, what we observe for RNNs is that they're going to capture dependencies that are entirely based on the data and the objective. So if they need to, never really look at things that are more than 5 or 6 words back and to be a good language model, then they're not really going to remember that information in any useful way. And people have like tried to visualize this by looking at sort of the gradients of those dependencies as you make them longer and longer in language models. But that's really kind of like meta-analysis. So in practice, the bound still exists, but unlike an order n or order k Markov assumption, You don't need to provide it, the data provides it when you're training the model. It's a function of your data, of the size of your model, of the complexity of your gating architecture. And in a sense, that's really the main thing that differentiates an LSTM from a simpler RNN, is that they make it easier during inference, during training, to capture longer range dependencies, but they're similarly expressive. So you can do language modeling with an RNN, and you can condition through the previous state on the history of the sequence, the unbounded history of the sequence. But because we're doing everything in vectors, right, and these are sort of nameless and abstract features, these vectors can actually represent information that is beyond the boundary of the sequence, that's just information from another part of your data, right? So you could imagine that you have some random information beta, and this could be another sentence, it could be a representation of the topic of the document, it could be the sentence you want to translate. I mean, this is basically the basis of sequence-to-sequence modeling, as we'll see in a second, and produce an embedding of that and just say, this is the start state of my language model. And now I'm producing my conditional probability that factorizes is actually expressing a global probability over this string, giving this conditioning information beta. And you could, as I said, condition by setting that as the start state, or you could feed it as an additional input. The nice thing about neural networks is that you can be really flexible with this kind of like network topology and explore different variants on the models without really needing to think about it in too much detail. And the model will just like work around it as long as everything's end-to-end differentiable. So this idea of conditioning on some information to train a conditional language model has yielded a variety of really interesting applications of this kind of architecture or set of architectures by using conditional language models to do transduction. And it turns out a lot of problems in natural language processing, but also other areas, are castable as transduction problems, as transforming one sequence or several sequences or other modalities, such as images of data, into another kind of modality. So transducing French into English, transducing code into the results, transducing an image into captions. Translation, parsing, computation, all these things are sort of transduction, and therefore something that you can express using this fairly general framework of conditional language modeling. So it's really cool. We've gone from something which is just, okay, here's the basis for unsupervised learning as adapted to text, to a very simple kind of architecture that you can use for all sorts of actual tasks you might care about if you think language modeling itself is boring, which most sensible people do. So again, you've probably seen sequence-to-sequence mapping in Oriel's lecture. I'll quickly revisit it in my own sort of formalization, and then we'll get onto some applications specific to language. Are there any questions before I jump into this? Okay, so transduction or sequence-to-sequence mapping is the goal of transforming some source sequence of information, so some symbols from a source domain, into a target sequence. And typically how this will work is we're going to construct a representation for our source sequence, our conditioning information S, and we're going to model the conditional probability of the next target word in the target sequence given the target words you've generated thus far. So this allows us to specify a very simple informal algorithm where you read in your source sequence, or perhaps read in the source image, or however you want to encode that source information to produce the representation of the source. And then you train a model simply to maximize the likelihood of your target sequence conditioned on that information. And at test time, you'll once again encode whatever conditioning information you have, like a new image or a new sentence of French. And then you can generate the target sequence using greedy methods, beam search, or a variety of search processes guided by that conditional probability distribution you're learning. So the obvious sort of, the very famous approach, although it was by no means the first approach to sequence-to-sequence mapping using neural networks, is in this paper by Skeever and Co. in 2014. So here we're going to be learning a conditional model over English given some French conditioning sentences, which is effectively what translation is in a very simple way. How this works is you'll have your source sequence of French tokens, and you'll embed the individual words and feed them into a recurrent neural network, and then just tick that network forward, so updating the representations based on the prefix you've read so far, and ignoring the output because it doesn't matter during the encoding phase. All we care about is the final representation of that conditioning information. And then you can actually use the same network if you have, for example, an explicit separator symbol or a different network with a different topology, etc., to start decoding. So conditioned on the representation you've had at the end of your encoder, you can start outputting the words of the translation, which are during training observed and during test are going to be sampled. And typically you will take the sampled word and feed it back in as input autoregressively during test time, and during training time you'll feed in always the correct word regardless of how the distribution looks, in order to condition the information on the sort of like a stochastic choice that was made in the output. So simply by maximizing the likelihood of the target words conditioned on the source information, we have a perfectly functional translation model, which works impressively well given how simple it is compared to a lot of the machine translation that existed before. So there are some issues with this very, very simple model, though, that were sort of, I guess, glossed over when it was initially presented. But a lot of the recent developments, and by recent I mean over the last 3 years, or 4 years now almost, in neural machine translation have come out of trying to overcome this problem. Is that if you just do sequence-to-sequence modeling like I described, you have this bottleneck between the source and the target, which means all the information from the source needs to be contained in the activations of your neural network at the boundary between the two sentences. So this is a problem of non-adaptive capacity. So for the same reason that it's unreasonable to expect the activations of an RNN to model a completely unbounded prefix, here it's unreasonable for them to be able to compress, because that's effectively what this is, the information from source sequences of unbounded length. Right? So the longer and the longer your sentences are, the more your fixed size information reservoir is going to fill up to the point where you assume that there's going to be some compressive loss as it tries to decompress it into the target language. This also causes problems during parameter inference. So we find that the target sequence modeling in this architecture is dominated, the modeling of the target sequence language dominates training. What this means is if you're training a sequence-to-sequence model without attention, like just with this kind of structure, and at random points during training you say, okay, let me test it, let me just feed in a sentence of French, you'll see that during maybe the first like 80 or 90% of your training time, the sentences that will come out will be English, will be correct, fluent English. That will happen actually fairly early on in training. It will start producing things that look like English. But that English translation won't have any relation to the French text. So it's learning a marginal language model before it starts to actually learn the conditional model. And the last bit of training, and usually quite far on in, is learning to propagate learn the dependencies between the source and the target. And this is simply because you can observe here what the model observes, where the stochastic choices are sort of realized, is only on the target side, right? So the only point you get error in the cross entropy between the distribution over what word belongs here and what word belongs here is when you're decoding, which means that the parameters of this whole section of the network and the embeddings of the source words and the dependencies between this position and the end all have to go through a bunch of nonlinearities, which we know typically squash or cause vanishing or exploding grading issues. So the noise, the gradient is going to become more and more unstable or typically reduced norm for most RNNs as it goes back through time, such that you're getting very good updates here in learning of the target marginal language model, and only because eventually the gradient is sufficiently sort of noiseless, or the expectation is sufficiently close to what you're actually trying to adjust the model to, does the encoder learn to act appropriately and condition the model. So in a sense, this fixed size assumption, this bottleneck you have between source and target, is one of the main reasons that it's almost amazing that this worked in the first place. It worked despite its architecture. So you have covered, again, sorry to keep on asking this, I should have just looked at the slides. You've covered attention in some form. No, okay. You've not seen attention. Wonderful. Okay. So attention is one very powerful solution to this that's inspired by traditional machine translation approaches where a separate tool typically would provide an alignment matrix. So when you have observed source and target strings, you could have a set of probabilities over which words in your source target align to which words in your target. And a lot of the traditional statistical machine translation models, like IBM's model 3 onwards or 2 onwards, incorporate that information. So alignment's a soft, latent way of conditioning on the sort of alignments that exist between target words and source words. And for some language pairs, these alignments are almost one-to-one. If you're translating, English into German or French into English, languages that are very sort of closely related within the Indo-European family and have a sort of very recent common ancestor relative to, for example, Mandarin and English, it's almost like if you translate the words individually and roughly reorder them, you're good. And that's what models effectively are doing. So attention works like this. Assume that you have an array of vectors produced by the encoder that represents some data. And obviously we have that in this case. When we are encoding, we're only using this red vector to decode, right? That's the state that matters. But you need to save the state of all the previous vectors in memory because you're going to backpropagate, and you're going to need the state of those activations in order to properly calculate gradients. So you have all this information sitting around in memory, and attention is just about using that. Assume you have that matrix that represents some data, and also the position matters. So just like here, you have a set of vectors, and these two vectors here correspond to this word here. So the position is important. Your controller is so the decoder cell is now, think of it as a controller, and that's a controller that's dealing with input and output logic in your model, right? In the very trivial case, it's just dealing with, okay, here's the last word I translated, and here's what I was doing before, here's my internal state, so I'm going to predict what word to do next. But now it has access to an extra component, which is this array of vector, which is like a read-only memory, if you will. And you want to read that data array at each time step using the controller in order to make better predictions about what you're doing. And in turn, this means because you're reading the memory, and if you do this through a differential operation, you can accumulate gradients in your memory and then use those as well. So if you really want to think about this as like as an API, removing ourselves from the specific way that attention might be done in this or that paper, or what controller you use, whether you use an LSTM or an RNN or a GRU, attention kind of broadly has 2 forms. And note that both of these forms, which I'll show you the second one of in a second, are themselves kind of RNNs, right? They have inputs and outputs, so everything inside this box is like a very structured recurrent cell. And they have previous state and next states, and you're going to be updating those. So early fusion is going to be the approach where at each time step you observe an input, so let's say the previous word that you just translated in your English sentence. And based on your previous state, so on the previous state of your controller, you're going to read something from the memory and combine it with your input. You'll update the controller state, which you'll then pass back with the current state of the memory as the next state of the overall recurrence. And you'll make a prediction on the output. So early fusion is basically, I look at what I've just translated, I look at what I have left to translate, I update my sort of internal state, and I predict what the next word should be. I will not read through the mathematics here, but it's here for your, if you want to look at roughly a formalization of it in your own time. Late fusion is a very, very closely related approach. So in this case, I read an input into my controller, and based on the previous state of my controller, I update my internal state. So I look at the word I just translated, and I update my internal state based on what I think I have left to translate in my head. And now I've updated my state, I look at the memory and directly pick the word that's the next word to translate, and then based on my current state and that selection, I pick an output. And so that's basically a lot. These are almost trivial differences, except early fusion has you're attending before nonlinearity, and late fusion after the nonlinearity. So they have pros and cons in terms of expressivity and gradients, but they're both very similar when it comes to translation. So equally, these are formalized here. And the concept of attention, do people want me to talk through the actual operation of attention? I don't want to rush over this. Raise your hand if you actually want to get the dirty details right now. Okay, someone's raised their hand. Tough luck, everyone else. Okay, let's do late attention because that's easier. So my previous state has two components here. It has the previous state, little ht minus 1 of my controller, so that's the previous state of your RNN. And it has my memory, so my array of vectors I have from the encoder. And so I don't put a temporal index on those because these are going to be unchanged. Once the encoder has been run, that is the same during every step of decoding. I'm trying to remember what exactly I wrote here. So I'm going to, this looks like an N, but it should be an H. I'll fix that. So I'm going to, sorry. Yes, I remember what I wrote. So I am using my controller update logic, so this will simply be an LSTM update or an RNN update, depending on the nature of my controller, based on the currently read symbol, which is the previously translated symbol, and the RNN's previous state. I will update my controller logic and have a vector which is kind of the intent of what I want to translate. Then I will pack that updated internal state along with the state of my memory as the next state for the recurrence. And here's where the attention comes in. I'm going to have, based on the current state of my RNN and my attention matrix, I'm going to apply a differentiable function which will produce a vector. And so how this typically works, and I'll just sketch it out verbally because there are so many variants, is assume I have some way, given my current vector, which I will treat as a query. So imagine this is my query vector, and I want to retrieve something from the memory using it. I'm going to see how similar that query vector, or some transformation thereof, is to each position in my attention matrix. So that's going to give me a single number. For example, I'll take an inner product. And I want to turn that set of numbers into a distribution over positions of my attention matrix. So what the easy thing you can do is apply a softmax operation. So the numbers I've computed through that similarity kernel become just the logits to my softmax. So then I have a distribution over positions. And now if this was an actual lane variable model, what I could do is sample a vector according to that distribution and say that's the return from my query, right? That's what my memory has returned. But that, while we do have inference methods to deal with that, like reinforce, or you could try and approximate the marginalization of that decision, instead we've postulated a mean field approximation where we're simply going to take a weighted sum of all the vectors in my memory, weighted by how much it's supposed to be returned. So that's basically taking the expectation of the vector according to that distribution. And so that vector is what will be returned by this section. I'll combine it with this according to a composition function, like an NLP or whatever, and then just predict the next word. So in a sense, the logic here is fairly simple, and if it takes a while for you after to stare at it until you can convince yourself that it's basically just like, here's some information, give me a vector back, and then I use that to predict. It's just peeking at the memory, right? That's just the nicety of this. Because all these operations like attending and then combining are typically linear operations, so softmax and inner products or MLPs, the whole thing is end-to-end differentiable so that you're passing gradient throughout your system when you're doing this. So I'll talk a bit about some applications of sequence-to-sequence and attention in NLP now to make this a bit more concrete. The first is skipping this bottleneck. So as I said, this bottleneck is annoying because we have all this redundant computation that happens before the vector in red, but we only condition on the vector in red, and that causes a bunch of nasty issues. So if instead at each stage here, before predicting the next word, I got to look at what happened before, which is my attention matrix, using the logic of my RNN at this state, I could capture longer range dependencies instead of doing it through my own internal dependency tracking mechanisms within the RNN based on the representations that were produced earlier, which is effectively what we want. So attention does look a little like that. Is that at each stage when I'm about to make a prediction, whether I use early or late attention, I'm conditioning on all the information before and filtering out those I think are salient based on my current representation. Because that operation is differentiable, the gradient not only flows through the computation that's happening in the RNN, so those are the paths where you're expecting the gradient to be attenuated, but also through these green lines here. At each stage where I'm comparing against all the previous vectors in my attention matrix in order to decide which word to translate, because that's a differentiable operation, I get gradient that immediately flows back to, let's say, the first word in the sentence and completely skips the bottleneck. So by having a memory that you can attend to, that you can look back into, you're not only solving a forward problem that you can capture long-range dependencies more easily, but training becomes easier. You have a channel where gradient can pass without as much noise back into the encoder and help you train the encoder faster, which, surprise, surprise, allows you to train your overall translation system significantly faster as well. Another cool application of this, and not just of attention, but of sequence modeling, is textual entailment. So this is moving a bit away from the language modeling objective, but using the exact same architecture. And this is really one of the strengths of neural sequence modeling, is that the same architectures that work for translation might require complete retraining, but they're typically a good starting point to do completely different tasks like parsing or textual entailment, which in traditional approaches might have required a very different approach built on, like, I'm going to use the parse information differently and come up with a new algorithm, etc. So textual entailment is a pretty cool task, and it's structured like this. You have two components. One is a premise, so that's a sentence that you are told is true, and then you have a hypothesis. And what you need to do is classify the relation of the hypothesis to the premise. So here I'll give you some examples. I have a premise here and three hypotheses that you have to separately classify. The premise is a wedding party is taking pictures. And a first hypothesis is there is a funeral. So this sentence obviously isn't really consistent with there being a wedding party taking pictures. So I could say that that statement is contradicted by the hypothesis or vice versa. There's a second sentence, which is they are outside. So this is where it gets a little more fine-grained, is that sentence is actually quite plausible for a wedding party, right? If you really let your prior knowledge of wedding parties, or in fact the knowledge that's in the data, inform your model, you might be like, okay, that's really plausible. But from a logical perspective, that's neutral. It could either be the case or it could not be the case. It's not directly entailed by the premise. And then finally, we have the hypothesis someone got married, which is trivially entailed by the premise. And in this case, requires a little bit of external knowledge, like, for example, the relations between weddings and people getting married. You have another one, a man is crowd surfing at a concert. That's obviously, if the hypothesis is the man is at a football game, there's a contradiction, unless it's a really, really specific kind of concert. I guess the Super Bowl, right? Okay. The man is drunk. This is really plausible, but again, that's we're talking about logical entailment here. So plausibility is something that you almost have to resist within your model. And so models that exploit just raw statistics might get this wrong. And then the man is at a concert is trivially follows from that. So you understand this. You get two sentences and you need to classify into two or three categories. Sometimes some versions of this task differentiate entailment from reverse entailment, which is the case where the hypothesis entails the premise or the premise entails the hypothesis, and you need to distinguish this. But in this wonderful data set by Stan Bauman from 2015, SNLI, you only had these three classes. So there are a variety of approaches you can do here that involve attention and that look a lot like translation models but aren't translation models. So my intern Tim Hochtaschel a few years ago worked on these models. You'd simply take an LSTM and instead of translating the premise into the hypothesis, you simply just encode both of them, except while we're reading the hypothesis, you get to attend back to the premise. So this seems a little different than what we're doing in machine translation, although if you look at the model topology and you squint at it, it's almost exactly the same thing as translation, except we're only predicting that class based on the final state. But while we're reading, we're using attention for a different purpose. And this is nice because we have attention, we can, instead of having the model having to decide entailment or contradiction just through the dynamics of the RNN, it gets to look for things that it thinks indicates contradiction or entailment almost component-wise. So for example, we can visualize these as heat maps. So here if we have as a premise, sorry, you have to sort of tilt, I'll read it out for you. The premise is a young girl kisses a ring-bearing boy at a wedding, and the hypothesis is two kids are playing tag. And so here it sees as strong indicators for entailment, the kids mapping to kisses and boy, sorry, to girl and boy. So it can split those dependencies. It also sees perhaps as an indicator against entailment that they're playing tag. Yes, I think that's probably rejecting it. But so you can try and understand what the model is basing its decision on, and obviously the presence of this quantitatively helps the model distinguish entailment from contradiction, from rejection. And while this looks like an alignment matrix, while it looks like these are word-to-word correspondences, remember that these models, when it's doing attention, and you can try bidirectional LSTM variants here too, are also conditioning on all the words around them, or at least in the prefix. So there's already some disambiguation baked in, right? It's like when it sees girl and it compares it to kids, it's like it sees girl conditioned on a young and kids conditioned on two. So they have this like richness that you don't have in simple sort of models based on parsers. Again, sequence-to-sequence models using the exact same architectures we've used for translation have been used for a variety of other approaches, like large-scale supervised reading comprehension. So testing and training, so training models to answer questions conditioned on documents, and therefore being able to read and arguably understand some aspect of the document because they can answer questions about them. So how this works is, imagine that you have, the task is you're going to see a document, you're going to see a question, and you're going to need to produce an answer. This, if you really want to look at it under the view of translation, is a translation problem. You're translating the document and the question as a source into your target, which is the answer. The questions are typically, in this formulation of the task, closed form, so fill in the gaps, but other data sets have other sort of variants on this. And here too, attention as you know it from textual entailment and translation can be adapted quite well. So you can read a document with a big LSTM. You can read your question with a big LSTM. And while you're reading the question, you can attend over the document several times to try and see, it's like, okay, maybe this is the answer, maybe this is the answer. And then at the end, decide what you think the answer is, which again allows us to produce really nice heat maps. So attention now can tell you a little bit, and obviously there's other parts of the model which aren't visualized in this, but we can somewhat peek under the hood to see when it's trying to answer a particular entity and identify a deceased sailor as X, it attends to several possible candidates, and only through reading the question iteratively will center on the correct answer. We've anonymized the entities within the stories, not because of privacy concerns, but because this prevents very drastic overfitting, and this is a fairly common technique in these kind of tasks. Any questions on that before I move to the final section? Are you just all subdued, or is this really all very sensible and very well explained? Just nod. Okay, if you have any questions after, you can come to me at the end of the lecture. So as a final sort of like stop on our, what metaphor am I going for here? On our train ride to understanding language with neural networks, I want to finish by talking about composition. So we've talked about words, we've talked about tasks that involve transforming words, and underneath those tasks, there's typically the need to be able to condition on larger units of text that we embed with LSTMs. But there are obviously other ways to produce representations of like the source text or of an image or of conditioning information. And that sort of falls under the sort of topic in natural language understanding of compositionality or composition. So how do parts like words or characters combine into wholes which are more than the sum of the parts? So obviously a sentence is made out of words, but it's not, the order matters. The presence of other words disambiguates. So composition plays a very rich role in how we understand cognitively sentences. And so how can we model this with neural networks or other methods? And I'll talk about this a bit from under the view of classification, since we've focused so far on transduction or sequence-to-sequence modeling, although we did see a few classification tasks. So textual classification involves the prediction of a label, such as, it's like positive or negative, or a scalar value, which is how likely, for example, a tweet is to be coming from a bot versus from a human. These labels or scalar values are predicted from a sentence or a set of sentences or a set of documents, depending on your task. And so typically, what you want to do is you want to produce a representation of your documents or your sentences or your phrases, and then use to jointly learn a task-specific representation and a classifier from that representation to your label, so that you can solve your task. Yeah, that's more or less what I said in much more words. So how can we produce a representation of a sentence if you have representations of words which you're either jointly updating or that you obtained from a word embedding method, such as those that we've explored at the beginning of this lecture? Well, there's a variety of algebraic operations that you could do before you jump straight into neural networks. The most trivial one is you could just take the sum of all the vectors or their mean. You could take the product of all the vectors, component-wise. Or if you think, okay, I want something really simple and algebraic, but not relying on commutative operations, so trivially the first two options will destroy word order, so you're guaranteed to have the exact same sentence representation for man bites dog and dog bites man. And that might lead to some confusion for your classifier if you encounter that sort of sentence. You can do things like this, which is, for example, sum across all the pairs of words in your sentences and apply tanh or sigmoids or sort of symmetry breaking operations that will make the whole thing not entirely commutative. So these are all very, very sort of simple operations that we understand algebraically. They're fast. And they don't add parameters. I mean, the only parameters are your embedding matrix. So here the representations that you learn under the constraint of the combination operation do all the work. You might think, okay, this is just like a weird preliminary to the more sophisticated composition operations that Ed's about to present, and you'd be partially right. But it turns out that this is a very sensible first thing to try. I mean, just like aggregate all your vectors with a sum or a product or a mean, and then just have a linear projection into your labels. That should be the first thing you implement, because A, it will take like 3 minutes, and B, it might work. And if it works really well, then you know that either your task is very simple and you know how to interpret the gains you get with a model that took you 3 weeks to implement, or it might be if you're in a business and this is like sufficient results for your application, then why would you do something that's going to require a GPU when you have something that takes like a microsecond to compute? So always try really simple composition methods first, because they frequently work very well. And you'll see frequently in the literature people referring to like bag of vector methods, where they sum or mean the vectors in a word as a sensible baseline. So do implement that as a baseline. So as a con, obviously this is not very flexible in that you can't incorporate syntactic information. It's dubious that it's certainly not going to capture word order. It's dubious that it's going to capture any sort of disambiguating effect, although maybe the product will allow you to say things with a low norm are going to become even lower, and that will work. And it puts a large, you're putting all the sort of work from your model into the representation, so that is going to be limited in terms of the expressivity of your model. So the solution could be do what we did in sequence-to-sequence modeling. Just run an RNN over your sentence and use the final state, or use a bidirectional RNN, or use a bidirectional LSTM, or use a neural Turing machine, or whatever you want. Like a really structured recurrent model could probably produce a very good representation of the sentence. And that's a perfectly sensible thing to do. But what other options are there that might use information that we might have handy? And so the sort of two kind of models I'll get at today in the remaining part of this lecture before concluding center around the use of trees. And these people, natural language processing people, especially with the advent of LSTMs and deep learning methods, have had a bit of an on and off relationship with trees, where initially people were like, okay, let's use trees to guide neural networks, and then everyone was like, okay, well, it's like we can translate with LSTM, so syntax is dead, and we don't need to use trees anymore. And now everyone's like, okay, maybe we should be using trees again. It's like it turns out it's a very good inductive bias. And if you're doing, maybe for language this is difficult because we don't know the true grammar of of English or other languages, and we usually have to train a model on that and all that. But imagine you're running a neural network that needs to produce a representation of logical expressions or code or math, or needs to generate code. For all these formal domains, we know the exact syntax and the relation between syntax and semantics, so why not exploit it? I mean, it would be crazy to say we have this information, but the LS team doesn't need it, so let's just use the LS team. So trees are back, and I'll give you a quick snapshot of 2 ways in which you can use trees. But before, as an introduction, in case you really have never taken a class in linguistics, many linguists believe that language is tree structured. And by that we mean that underneath the surface form of an expression like the old cat ate, I didn't pick the sentence, I think Sam did. It's a weird sentence. Underneath the surface form of this string, there's a latent tree, or perhaps several trees, that guide our interpretation or understanding of this sentence. So each sentence has a latent parse tree or distribution over trees. And the tree tells us syntactic information, so like that the is a determiner, old is an adjective, cat's a noun. It gives us combinatorial information that, for example, old applies to cat because both combine to form a noun phrase or proto-noun phrase. That the noun phrase is only typed correctly or valid if there's a determiner in this case, and that noun phrase is the subject of ate because it combines to form a sentence. So syntax isn't just about like type checking your natural language, it's also about trying to understand the relational information expressed in the sentence. And obviously there exist parsers, and there's a large body of literature from decades and decades of natural language processing and linguistics. But there exist statistically driven tools that are very accurate for languages like English and not so accurate for other languages, that give us a distribution over possible parse trees given sentences that allow us to get trees on the fly for sentences in your training set. Yes?
If you have your old statistical model that builds your parse tree, is it possible to kind of in the same way you retrain a given embedding, you retrain the way in which, or you allow your
That's a great question. We'll, in a sense, get to that in about 2 slides. But yeah, there has been work on neural networks augmenting statistical parsers, and you could imagine formulating a completely end-to-end model. And I guess we'll see a variant of that in a minute, where you're jointly learning the parser and the actual composition function. But let's start for the case. Let's start by assuming that we do have parsers that we don't care how they're built, but that give us like a tree for sentences. And now the question we want to answer is, how do we use this information, this added information, in addition to the words in my sentence and their order? How do I use this structure in order to guide composition? So the very basic idea behind tree RNNs, so they are they're recursive rather than recurrent neural networks, but trivially an RNN as in a recurrent neural network is also a tree RNN with left branching. Or right branching, I can't remember which, but it's, you combine, and the tree is always the same. But the basic idea is you're going to use a sample to the maximum likely parse tree that your parser gives you to guide composition by applying a function to produce a representation of a parent in the tree given its children. So for example, in this case, we would start by producing embeddings for the, old, and cat, and ate. And let's take the simplest case where there's just one composition function and our parse tree is conveniently binarized, which means there's always 2 children, which conveniently is the case in my example. But obviously you need to figure it out how to deal with the case where it's not binarized. So I have the vector for old and cat, and I have my composition function, which is going to, let's say, concatenate them and project them through an NLP to produce a single vector for old cat, which is in the same size or space, because it's obviously going to be recursive. Then I have a vector for the, and my vector for old and cat. I apply that same function, get a vector for the old cat, and do this again for the old cat and 8 to get the vector for my sentence. So this is just like very much like an RNN. A recurrent neural network is taking a repeated unit of computation and unrolling it across a sentence to dynamically produce a neural network based on the length of your sentence. A recursive neural network, or tree RNN, which they are now all called tree RNNs to avoid confusion, because RNN is taken, uses the syntax of the tree to dynamically produce the topology of your network with repeating units of computation. Now, because we not only know the topology of the tree, but usually we have type information. So for example, in this case, we know that there's a different sort of combination happening when I combine old and cat with the old cat. You can incorporate that by having the parent be a function not just of its children, but also of the type of the operation. Now, because there's usually in a grammar a limited number of these types of these operations, the way you typically implement this is just have a different composition function dependent on what the actual syntactic rule used to combine was. Does that make sense?
Do you then search through the different possibilities of combinations, or are you coding it explicitly?
So here we assume that we have the tree, right?
Oh, right.
And then you combine. If you have a distribution over trees, then you could take like the top k, or you could like do a Monte Carlo estimate and marginalize. But people typically assume that they just sampled the most likely tree, or just greedily took the most likely tree from the parser. So, I mean, here we've seen a very generic way of describing the composition, but this applies to pretty much every variant in this model, where this could be something like an NLP, like I suggested, or there have been more sophisticated composition methods that mimic what we do with LSTM, and GRUs, so where you have a cell and an actual activated state, and you do some gating. So there's tree LSTMs that are effectively the tree analog to LSTMs and RNNs, and those work very well in that they propagate gradient down nicely. But even without the tree LSTM, compared to an RNN, where the gradient has to go linear, like the distance the gradient has to go to capture a dependency is linear in the length of the sentence, here it's actually assuming a sort of vaguely balanced tree, log linear, and that's nice. Okay, so did I just describe this? Oh yes. So we have a variety of corpora where this, which we can use to train tree structured models. So obviously, you could just run a parser over any data if you have labeled data and then use this kind of method, but parsers aren't exactly perfectly accurate. So there's been a lot of work in like paying linguistics students in Stanford, I'm assuming an honest wage, to annotate corpora where we had objective labels of what the sentiment of an expression was. That's great because you have high quality annotations there, and you can even have like a variant on their corpus where there's sentiment labels on all the sub-phrases or the branches, so you can like do full supervision and all that. But technically, you don't need that sort of stuff anymore. And obviously, as I said, you can use parsers to annotate other text classification, and because it's training data, you can do that and ask your linguist to correct the parsers, because you still do need very clean data. The problem is you don't have, unless you're really rich, you don't have the luxury of having a linguist on hand at test time. So it's like you've trained your model on tree data, and then you got to do this on tweets and run it in the wild. And people write all sorts of different ways on Twitter that are going to probably break most statistical parsers. And even if it's not Twitter, and even if it's not sort of like slang, you're unlikely to have very, very, very high quality parsers for test data, and you don't have a linguist to fix it. So it can be quite difficult to actually run these at test time unless you have an idealized sort of test set. So the solution, well, one solution to this is to say, why don't we jointly train composition operations with a parser? So this is what Sam Bauman from NYU did 2 years back. So exploiting the fact that there's an isomorphism, so there's a structural identity between trees in a context tree grammar and sequences of shifts and reduces. So this is called shift-reduce parsing, and I'll briefly give you an example. So, like, if you're reading through the sequence, the cat sat down. Shift means that you're moving the sentence, you're moving things onto a buffer, and reduce means that you're doing a combination operation. So the branching structure of the tree actually directly and uniquely translates into 2 times t minus 1 shift-reduce operations for t words in the sentence. Actually, I'll give you an example in a second. So we have the cat sat down, and imagine that you know these shift-reduce operations because you knew the tree. Let's run through the actual running of the shift-reduce parser. Shift is going to, you have a stack which is your sort of working memory, and you have a buffer, which is all the words that you have left to process. So you're going to start by shifting the first word onto the stack, and then the shift reduce parser tells you that you're going to shift the second word onto the stack, and then reduce says that you're going to combine the top two words on the stack, in this case to apply a determiner to a noun and form a noun phrase. Then you're going to shift sat onto the stack, and then shift down onto the stack, and then reduce is going to combine the top two words, sat down, in order to form a verb phrase, and then finally another reduce will form the sentence from the noun phrase and the verb phrase. So this is just building another way of building the tree by linearizing the operations. So it turns out, if you imagine now, instead of words, these are the vectors for those words. Shifting is still going to be the same thing. You're just moving a vector from a buffer to a stack, and we can perfectly well do that. And reducing is going to be applying a composition function, so your tree RNN update or your tree LSTM update, and putting the composed vector back on the stack. Then we can see how this is going to be jointly. If you have some way of predicting the shift and reduce operations, you can jointly parse and compose, and then try and train both based on the representation you have at the end here. So the high-level idea, spin is about doing just that. At training time, you still have trees at training time, so you know the shift reduce ground truth. And conditioned on the vectors at the top of the stack and at the top of the buffer, independent of how many there are below those, you're going to have a neural network that decides shift or reduce, so that's binary classification, but we can train that because we observe the result of that classification during training, and you can just take Bernoulli cross entropy. And if we shift, we move the word embedding, and if we reduce, we compose. And the composition function is also differentiable. So because we know what the sentiment at the end of the result is, we know what the label at the end of the classification is. So if we predict the label based on this representation, then the cross entropy of the correct label compared to the distribution will backpropagate through all these composition operations. Shift is the identity, and then therefore we have gradient on every part of this operation with regard to the loss. So we're learning jointly a sentence representation from the classification loss and shift reduce from the parse. And both are jointly conditioned on the same word representation. So it's a powerful model that allows you to deal with trees when you don't have them at test time. And really quickly, I'm going to talk about the high-level sketch behind reinforcement learning spin. So this is a variant that Denny Yogatama postulated 2 years ago. So what if you don't want to have trees during training time? And this is the case if you don't have annotators to annotate your data set, so you don't have those shift and reduce operations. Or you might believe that linguists are wrong about the tree structure of your language and that that's providing unnecessary bias. So all you want in your model is to say that there is some tree structure underlying the expressions, but you want to jointly infer that structure, and also they actually learn to compose and predict. So we can take spin, the exact same model, and the only thing we're assuming we don't have is the training labels for shift and reduce. So now you're making a latent discrete decision during training. We have to actually sample from that distribution rather than take the actual true label. But that's the only component that's non-differentiable in our model. So you can use reinforce, so a reinforcement learning style objective, to estimate the gradients unbiasedly for that lane variable, while everything else stays the same. And what's the reward in this case, if you want to think about it in terms of reinforcement learning? Well, it's simply going to be the cross entropy of the negative cross entropy of the correct label. So the same objective we're minimizing through backprop for the rest of the model, whatever we're maximizing has to be minimized by whatever we're minimizing, the loss we're minimizing is going to be maximized by the reward model, because when you're minimizing the loss, you're maximizing the reward. And so this jointly learns to produce parse trees and exploit them during composition, unbiased by what linguists might think the trees should be. And it's interesting that it does produce some trees that resemble what linguists suggest, but sometimes it produces trees that don't fit our linguistic intuitions, but are actually significantly better for a particular task. So they might not be reusable. So just to really quickly wrap up, because I have like a minute left. Language is a super difficult topic, and we've only scratched the surface of some of the very simple issues that I could cover in a 2-hour lecture. As I said at the beginning, there are many natural language processing courses and that go into like the bleeding edge of research, including lectures by me and some of these. that are, I think, absolutely fascinating because they try and tackle sort of the very definition of intelligence and how we assess them. So I really recommend looking into this. And also, if you're interested in this field, know that it is really new, that there are so many open problems, some of which you've actually brought up in questions during this lecture. So there's many opportunities for progress, which is always a good thing to hear if you're interested in continuing doing research on a topic. So I encourage you to look into it if your appetite has been whet by this lecture and explore the detailed and open arena that is NLP with deep learning. Thank you.